All right, let's get going. Happy Monday. So first things first, I granted a couple of extensions on homework till the end of the day, or let's just make it tomorrow morning, 9 a.m. So as long as you submit your updates, whatever it is that you missed printing, whatever it is that you missed, you can submit it till tomorrow, 9 a.m. Okay, so we get that taken care of. Question, is there any, I posted one video that was missing, or rather makeup for it. Anything else that you have noticed in terms of study guides that you're missing? I thought I posted everything last Monday in terms of practice exams. Did I miss anything? Are you missing anything other than talent? For study. I don't know how to answer that one. I don't know how to make up for that one. I'm still learning. But at some point you just have to think to yourself, let it go, let it go. Okay. So I cannot give you time, but I can give you all kinds of study materials. So let me know if you're missing anything. Again, I'm going to have office hours at 4 to 5 today. I apologize for the last moment move. All right, so let's get back to the formulation of our system. So we have gone through all kinds of ways to solve system. Gaussian elimination with pivoting, without pivoting, then LU decomposition, and so forth. All of those were methods for solving. Some of them, we did all of them by hand, then we programmed them. You know how to use pre-programmed stuff by now. So you should be good to go. If I give you a linear system, you should know how to figure out where to solve it and how. Okay? Whether it's by hand or not by hand. Now, question is, well, how do you come up with linear systems? Are they all those where you come up with matrix A, 1, 2, 3, 4, 5, 6, 7, 8, 9, because you can't come up with anything better? Or how do we actually come up with the systems? So that's what we were started last time, and we're just going to basically wrap up today. And one of the most common, so there are two main ways to come up with a linear system of equations, or any system of equations. One is the basically balance of forces. So any kind of force balances that we've been working on in solids or statics or both, they will actually often come up with systems of linear equations. Okay. What we did in class last time was that like movement of fluids through a reactor system, and basically in steady state, you expect that whatever comes in is what comes out. In equals to out is an equation once you express what that influx is and outflux is for every node in the system, as well as for the system overall. Same thing would be the balance of forces. Just give me 1 second. So basically, whatever forces you have, when you sum them up, typically you have to have it in the coordinate system. So you go coordinate by coordinate, you have to have a balance. So some sum of forces has to be equal to 0. That's an equation, right? So all of these things are typically giving us linear equations. And if they're non-linear, we often actually linearize them, okay? Especially when I have a system. Now, your question.
Oh, are these simple problems going to be on the test?
Formulation? No. Formulation, save for the final. So I gave you 2 example tests. And on both of them, it says on the formulation problem, save for final. So save it for final and practice it for final. Okay? So formulation, no. The last thing that will be on the test is LU decomposition. Okay? Any other? So let's just quickly recap. Other than balances of various forces or fluxes or whatever it might be that we have physically going on, discretization of differential equation is another and probably the major source of systems of linear equations. So how does it go? This is one simple example. I'm typically not going to ask you to solve differential equation analytically. You have a course that does precisely that. Okay. So I typically refrain from testing you how well are you doing in differential equation in this course. I want you to actually just understand, well, okay, it's important to do analytic solutions as well, because otherwise we can't test our numerical solutions. But the majority of equations out there, we will not be able to solve analytically. This doesn't diminish the importance of analytical solutions. We're still going to go to them, and they're still very important. But in major number of problems, we actually have to solve them numerically. So how do we go about it? Let's say that I have a simple heat transfer problem, such as the one here. I have a heated rod, and that rod is going, does everybody see my mouse? Okay, I have a rod, okay, and I'm doing a one-dimensional representation of that rod. Every discretization starts with saying, okay, we're going to, instead of looking at this as a continuous rod, we're going to sample a number of points, typically in regular intervals, or rather we do it in regular intervals if we can get away with it, because that's the simplest. Okay? So if you were programming it, and let's say that this interval is between 0 and 10 in x, what are you going to use to numerically sample points between 0 and 10? What function in Python? Hey, that's why we needed it. That's why we did that first, to have that tool. So basically either least space or a range, one of the two, whichever one you typically prefer, and given what's actually given in the problem, number of points or the delta between them. Okay. So here we have delta x of 2 meters, right? So, okay, so you sample those number of points, and when we're looking to solve for temperature, okay, what we're actually looking for is precise temperatures at these discretized points. So my solution, numerical solution to this problem is basically T0, T1, T2, T3, T4, T5, where my T5 is T of x5, or T4 is T of x4, which we in general say Ti is T of xi. Okay? Excellent. So that's what we're looking for. So how do we set up equations for those T's? I have a differential equation that has to be valid at every point, whether it's this discrete point or some point in between. The way differential equations work, they work for the entire set of points in some domain, continuous domain, right? And the only place where I could have issue are the boundaries, which is why we need boundary conditions. So here, my boundary conditions are this wall on the left that is kept at 40 Celsius degrees, and the other one on the right that is kept at 200 Celsius degrees. So that gives me my T0, T of x0, and T5, which is T of x5. The 4 in between we have to find, and we have to set up the equations for. I know that my d squared t dx squared, so the second order derivative in temperature, plus whatever transfer is happening between the rod and the surrounding air, which is at 20 Celsius degrees. So in this setup, I actually have this h is experimentally measured, and it's given right up there, okay? So h is 0.01 meter, and this is something that depends, meter to the minus 2. This is something that depends on the materials in contact. The more similar the materials, the faster this transfer happens, and I might even have a continuous boundary. But whenever I have solid and liquid or fluid in general, okay, it's not going to happen immediately, so we have this transfer that happens with h, and it's faster if the difference between those temperatures is bigger, which is this Ta minus T. Okay? So typically, if I have two solids in contact, I'm going to assume a continuous boundary. All right. So anyway, if this wasn't here, I would simply have a linear equation in T as a solution. So I would just do my linear solution in between T0 and T5, and I'd be done with it. But that's not the case. So I have this nonlinear part in there. So how do we set up the equations? We approximate the differential operator at that point using the nearby points with the discretization as I set it up for the problem. So I'm going to approximate d squared t dx squared as, so let's look at this point 1. It's going to be t of x2, which is my x plus delta x, right? Minus 2t of x plus t of x minus delta x, which is t of x0 in this case, divided by delta x squared. Okay? So I'm going to simply go and replace that in this equation. Okay? And that's what we've done here. We applied this differential operator at this point x1, and my mouse is always a little delayed with the screen. And now completely missing. All right, I'm going to point. So basically, that's what I've done here. So x1 plus delta x is x2, and x1 minus delta x is x0. And then I write that out. In here, I know everything other than t1 and t2. I know t0, that's my boundary condition. I know h, I know delta x squared. I know ta, that's my ambient air temperature, which is 20 degrees. So the only things that I don't know are t1 and t2, and I see that I have only numbers multiplying them. So it's a linear equation in t1 and t2. I don't have sine of t1, I don't have anything non-linear going on. Okay? So this is, I can work it out what it actually is, but it's a linear equation in t1 and t2. Okay? That's good, that's what I'm looking for. So now I just march through all 4 of them, okay, and do the same thing. So on my next go, okay, I'm going to have, let's see if my mouse woke up. No, it didn't. Oh, well, my mouse needs extra coffee. So I will have basically t of x3 minus 2t of x2 plus t of x1 divided by delta x squared plus h times Ta, which is my 20 Celsius degrees, minus t of x2, which is t2, is equal to 0. So this is going to be a linear equation in t1, t2, and t3. Okay? Then I'm going to move forward, and I'm going to have t of x4 minus 2t of x3 plus 2t of x2 divided by delta x squared. Okay? Plus h times Ta minus t of x3. Okay? So I'm going to have a linear relationship between T4, T3, and T2. Okay? And as always, I set everything that I don't know on the left-hand side and everything that I know on the right-hand side. And then I'm going to proceed to the final point, and I'm going to have T of x5, which is actually my boundary condition, so I know it. Okay? Minus 2t of x4 plus t of x3 divided by delta x squared plus h times Ta minus t4 is equal to 0. Does everybody see that? How it kind of repeats at every point. And key here, those are simple to set up. I can write them down, we can work them out. It's not a problem. Okay? Those are going to be 4 equations in 4 unknowns, t1, t2, t3, t4. Before we proceed, I'd like just to make one key observation is that the problem is that how do I set this up so that it works if I choose to discretize with 20 points in between? I'm not going to go right one by one, right? I have to set up a rule, okay? So it will have to go through a for loop to actually be a more organized solution that kind of works more effectively in more general situations. So that's something to think about. Okay? So in the case of T1 through, so you will always start by setting up a small system, but you should be already thinking like, how do I generalize this question?
Oh, I was just going to ask that.
Yeah, so that's the key, that's a challenge. And bigger of a challenge in all of the linear systems is I kind of like here they're linearly organized, so I'm looking for T1, T2, T3, T4, so that's my vector of unknowns. This is what we were calling x's. And all of our ax is equal to b. What are those x's? Okay. And bookkeeping of how do I arrange all of the things that I don't know into my x is actually can be really challenging. So let's say that we are solving in some world. I'm solving for the temperature and pressure in this room, and God forbid velocity as well. Okay. So first I'm going to discretize this room in the number of points. This is a three-dimensional room. Even if I set up only 9 points around here, like how do I organize them into this one vector and unknowns? Okay? So there's this bookkeeping going on between what do I place, and do I go by pressures first, temperatures first, velocities first, x, y, z components, right? So there's this bookkeeping part of how do I plug things into my vector of unknowns and how do I organize the system. That is, it should be easy, but it's not trivial, right? So conceptually it's easy, but how do I automate it becomes a problem. So that's something just to have in mind, that that's typically the most challenging part. How do you then debug? And hint, that's going to be part of your computational part. But you will work in teams, okay? So essentially, how do we work that out so that it's general enough and that it works in a different system? So let's just proceed with solving this problem. Okay, so at my node x2, I got something like this. So let's just quickly, so this is what we wrote down last time at node x2. So I'm going to, who can tell me what's going to happen at node x3? So if you this is very similar to this, but I'm going to write down the equation. So the equation is d squared t dx squared plus h ta minus t has to be true at every point. So this is my differential equation. And also the way I'm discretizing this is approximately t of x plus delta x minus 2t of x plus t of x minus delta x divided by delta x squared. So what do I do at x3? And I'm linearly arranged x0, x1, right? So those are all of my sort of quick reminders from the previous slide. So what is going to be this differential equation that I wrote down, d squared t dx squared plus h times ta minus t is equal to 0. What is it going to be for node x3?
D squared D3. D squared T.
T of x3 plus delta x, right? That's T4. T of x3, which is my T3, plus T of x3 minus delta x, correct? And that is, everybody sees that that's T2? Divided by delta x squared plus h ta minus t of x3, right? And that's my T3. So that is my T4. I'm going to multiply with delta x squared. T4 minus 2T3 plus T2 plus h delta x squared Ta minus T3 is equal to 0. Let's work this one out just to see what it is as numbers, just that numbers click in. So this is, whoops, whatever it is that I did here, I don't know. Okay. Right. So this is T2 Then I have with T3, I have minus 2 plus, what is H? It's 0.01, remember? What was delta X?
2.
2 meters, so 2 meters squared times 4, right? Times T3 plus T4. So those are all the things that I don't know on left-hand side, right? Is equal to, what is on the other side? This term I don't, that I know, right? Everything that I know goes on the right-hand side.
H delta X.
Yes?
Oh, TAH delta X. Sure.
Yes, so it's minus 0.01 times 4 times TA was 20. Okay. So this equation is actually T2 minus 2.04 T3 plus T4 is equal to, what is this, 80 minus 0.8? Yes? 80 times 0.01. And then this one up here, if you actually look at it, this one versus this one, they have the same structure. They're just shifted, right? Everybody sees that? So this one up here too is it's just T1 minus 2.04 T2 plus T3 is minus 0.8. And if I had more of them, of these internal ones, they would kind of all look the same. They would just kind of shift through. The only difference that I get is like those boundaries, the ones that are interacting with boundary conditions, such as the one at node x3. So let's write at node x4 rather. What do I get? The same equation will be T of x4 plus delta x, which is T5, right? But T5 I know, it's my boundary condition. Minus 2T4 plus T3 divided by delta x squared plus H times TA minus T4 is equal to 0. So what I don't know in that one are T3 and T4. T5 I know, so it's going to, and T4 once again. T5 I know, so it's going to have to go on the right-hand side, right? Any questions the way they're set up? Okay, so I'll just then give you how it looks like when it's cleaned up, which is somewhere in my notes. There we go. So when I clean it up, I'm going to really be left with the following. Minus 204 T1 plus T2, that was my first one, is equal to, that 40 Celsius degrees will go on the other side, so it's going to be minus 40.8. And then it's going to be T1 minus 2.04 T2 plus T3 is equal to minus 0.8. Plus T2. T2 minus 2.4 T3 plus T4 is equal to also minus 0.8. And the last one will be T3 minus 2.04 T4 is equal to minus 200 because I had 200 Celsius degrees as T5 going on the other side. And this is my system. How do I write it in terms of a matrix times the unknowns is equal to something on the right-hand side? My unknown vector is T1, T2, T3, T4. What is in the first row of the matrix? Then 1, then 0, 0. Yes? From the first equation. Do I have a plus minus something?
No, you can.
You good? I'm not always good, so it's good to double check. All right. Then I have 1 minus 204, 1, 0. Yes? Then I have a 0, 1, 1, and 0, 0, 1, minus 204. And I always manage to squish that last thing. And what is my vector on the other side? What's on the right-hand side? Everybody sees that? This you need to know for the test, how to go between the system of equations and the matrix form. Why? Because most of the software out there asks for matrix A and right-hand side B. And this is your X, right? Your unknowns, how you really call them internally. Yes? What is special about this matrix? It's tri-diagonal. For those of you who looked at the practice exams, it's tri-diagonal. It's faster to solve. So it has things living only on the, or non-zero, only on diagonal, main diagonal, one above, one below. Actually pretty simple too. These are all kind of constants, right? And the rest is 0. If it were bigger, if I went for more than 4 points in between, if it was 40, it would still look like this. It would have a whole lot of zeros. Yes? And on the right-hand side, it's this portion, this first one and the last one that are changed by the boundary conditions, because that's that known temperature that went on the right-hand side, but everything in between would be minus 0.8. Okay? So kind of see how I can actually do this in a for loop that give me any number of points in between. I can kind of write it down how it looks like, yes? So we're not going to go into solving this. This is just formulating. I know how to solve it. I can plug it into any of the solution software. Or if you're already ahead of the game and you looked at the practice exams, if not, I'm guessing this is the one I'm going to be solving during the review on Wednesday. Okay. Then you basically, actually, this is way faster to solve than the standard, because in every, so when I look at this, when I'm going to eliminate, I have only this one to eliminate. And I already have zeros here. So that's only one step, right? Then I move over here, I only have one row to eliminate, and everybody else is already 0 and so forth. So that's much faster. Okay? Questions? Give or take, this is the procedure that you use to discretize differential equations, so for with so-called finite differencing. And you will always end up with a system which is so-called sparse system. It has a lot of zeros. So discretization using finite differences results in a sparse, lots of zeros matrix with repetitive structure. And those are typically, if it's tridiagonal, even a pentadiagonal system, those are common. They're faster to solve. These systems, there's a whole line of specialized solvers that is way faster for any other regular system. There is a number of specialized and faster solvers for these systems. See posted practice exam. Huh?
What does it say after specialized?
Faster. This is why it's nice that most of the time I'm actually using the slides. My handwriting has gone, it's deteriorating as I'm getting older. It is hard to believe, but when I was an undergraduate student, there was no PowerPoints back then. And those who were keeping notes were in high demand. And I was actually one of those. My notes were always organized and my handwriting was actually legible back then. It's been a moment that it's just gone worse. Which is why I'm thankful for the PowerPoints and the automated note-taking. Okay, any questions about this? So again, you will get to practice this in your computational project. Okay? So with that, we're gonna move on with slightly different systems. Oh. Oops. Alright, so we have thus far covered so-called direct methods for solving systems of linear equations, Gaussian elimination or Gauss elimination, and LU decomposition. And in both cases, we are going to actually look for the actual solution. The only problem that can get in our way of getting that actual solution is roundoff error. And in your homework that some of you are possibly still working through, that first problem actually showed how bad it can get if you really didn't have a lot of storage for the roundoff error. Often we kind of don't notice because we do have way more than 4 decimal points, but that problem was supposed to exemplify what the difference could be. And you will actually always have those differences. They're just not going to always be super visible, but they can get pretty bad. So as I have large system, I have more and more of these roundoff errors that can actually really make the solution worse. So the more of these additions and subtractions and divisions and multiplications that I do, at every one of them I will have some roundoff error, and it can really pile up if I have a large system. So typically we need an alternative for systems that have more than 1,000 equations. And what we do is so-called indirect methods. They're very similar to actually our root finding, because this is a root finding of sorts. Okay? And one of the common ones is Jacobi Method, which basically just tries to figure out a way, can I start with solution, some guess, and then iterate and hopefully get better as I iterate. And Jacobi Method is actually an example of that. It somewhat resembles that fixed point method for root finding. I look at my system, and here I have a system that is 4 by 4. I look at my system, and I kind of rearrange it. So I leave, in this first equation, I leave a11x1, or rather this term, and I divide by a11, and I put everything else on the other side. And when I do that, I have b1 minus a12x2, a13x3, a14x4, and I divide it by a11. So I have x1 is equal to something else that doesn't depend on x1. And I do the same thing for x2 from the second equation. So I leave this term from the diagonal, and everybody else goes to the other side, and I divide by a22. And I proceed. It's kind of like a trick. So I have x is equal to something else. And when I look at this in vector form, this is a vector x, right, of unknowns. And this is a vector function of x. Does everybody see that? The vector x? So it looks like that x is equal to g of x. You have started reviewing root finding methods for Wednesday. Yes? So it looks a little bit like that fixed point. And the way that iteration started, well, it said, okay, well, let's start with some sort of guess for this. In this case, it's going to be for the vector x, not just for one value. And then compute what I have on the other side and replace that value with that and repeat. And that is indeed the Jacobi method here. It's just using vectors because I'm solving a system, not just looking for one single value root. Fine. And there are two variants of this method, but let's work through this Jacobi method first. Okay? So when I actually do that, okay, I'm going to again replace. So now I'm going to have xi to the k plus 1, which is my iteration. I have a vector. So instead of just using x0, x1, x2, x3 to number iterations, I'm going to put that in the superscript as my number of iterations. So k will be monitoring my number of iterations. And what I see here is that each xi is a bi, right? Minus sum of everybody else other than that I multiplied with corresponding aij from the previous iteration and divided by aii. Is everybody okay with the generalization? So this is just in terms of those sums of formulas. But conceptually, I start with a guess, and then I just compute what I have on the other side. I just rewrite the system, okay, and then proceed. So let's try this with a piece of paper and this system. So take a piece of paper, and this is just to make it simpler. You can ignore fourth row and fourth term, so I just use 3 by 3 to make it simpler. So my system that I'm solving is 3x1 minus 0.1x2 So without even looking at this system, just work with the system and express, in the first one, express 3x1 and put everything else on the right-hand side and divide by 3. Okay? That's what was done here just with general numbers. So it's 7.85, this is your B1 in this case. This all goes on the other side and divide by 3. So first up, set up a system of equations where you have x1, x2, x3 on the left-hand side and everything else right-hand side. Did everybody come up with the equations? Let me help up. Okay. So my first equation is 3x1 is equal to 7.85, in this case plus 0.1 x2 plus 0.2 x3. And I'm now in place going to divide by 3. Yes? Then how is the second one done? It's 7x2, so it's going to be something divided by 7. And what I have here is minus 19.3 minus 0.1 x1 plus 0.3 x3. Does everybody see that transition? So I took the diagonal element and I put everything else on the other side. And the last one will be this 10x3. So x3 is equal to something divided by 10. And that something is 17.14 minus 0.3 x1 plus 0.2 x2. Yes? So this is my vector x, sort of, is equal to some function. I'm going to write a g of x. Yes? Does everybody see that? That's how it's expressed. Vector equation. So this is similar to fixed point iteration. So that's just a side note. Now let's get back to the iteration. So I'm going to start this with a guess 0, 0, 0. Okay? So my initial guess is 0, 0, 0. In other words, this is my x1, 0, x2, 0, and x3, 0. Initial guess. Yes? So how do I get my second iteration or my one iteration? x1. So its first element I calculate from the first equation by plugging in a 0 in there. Yes? So that is 7.85 plus 0 plus 0 divided by 3. What is that? Can somebody help me out? I don't hear well. Actually don't. That's actually a true statement. 2.6. 2? Yeah, I'm going to leave it at that. The second one is just again plugging my initial guess for x1 and x3, which is both zeros, so that makes it easy. So it's minus 19.3 divided by 7. What is that? 7.6? Something like that? And the third one I know without a calculator. 71.4 minus 0 plus 0 divided by 10. I know how to divide by 10 without calculator. So that is my now iteration 1. How do I proceed to get iteration 2? So I'm going to plug in these numbers into same set of equations, right? Gonna x1, 2, okay, is 7.85 plus 0.1 times x2, which is now minus 2.76, right? Plus 0.2 times x3, which is 7.14 divided by 3. Yes? So I'm just using this and this in this equation. Right? And now it's just a little bit of bookkeeping to get that answer correct and not make a mistake. Then my this was x1 second, x2 second iteration, and x3 second iteration. I proceed the same way, so it's minus 19.3 minus 0.1 times, I'm going to just make it a plus here, 2.7, no, x1 is positive, never mind. It's going to be 62 plus 0.2 times 7.14 divided by 7.
0.3.
0.3, correct? Minus 0.3 times 2.62 plus 0.2 times negative 2.76 divided by 10. Anybody has Python up that's faster than a calculator in typing this in? Can we get the numbers? Can we get the numbers? How close is the first one to 3? Pretty close. Even the first guess was actually pretty close. Then mine, I had minus 2.6. That's not terrible for starting from 0. Okay? I had 7.14 even in the first guess, right? After plugging in the first guess. So this can actually converge pretty quickly, and therefore I'm going to have way less roundoff error, okay? And might get close to my solution by iterating, okay? So it's an alternative to Gauss elimination. Thank you.
How many iterations do we do normally? How many iterations?
Epsilon. I stop when I tell myself to.